Today, we're diving into an extraordinary breakthrough where neuroscience meets artificial intelligence. Researchers from Harvard University and Google DeepMind have achieved something remarkable. They've developed an artificial brain for a virtual rat that controls its movements in a highly realistic physics simulation. Published in the prestigious journal Nature, this groundbreaking work opens vast new possibilities for understanding how real brains function and control complex behaviors. It also hints at future advancements in robotics. Let's dive deep into the specifics of what the Harvard DeepMind team accomplished and why it's such a game-changing achievement. Firstly, the researchers tackled the immense task of creating an accurate virtual model of a rat's body within a sophisticated physics simulator called Majoko. This virtual rat had to adhere to the laws of physics, including gravity, friction, and the intricate mechanics of a real rodent's musculoskeletal system. To achieve this, the team utilized a vast dataset of high-resolution motion data, recorded from real rats engaged in various natural behaviors. This dataset provided crucial information to construct and validate their virtual rat model. However, simply having an anatomically precise rat body was just the beginning. The next challenge was to design an artificial neural network capable of learning to control the virtual body's biomechanics and reproduce the diverse movements observed in real biological data. Here's where Google DeepMind's expertise in machine learning came into play. Collaborating closely with Harvard, they applied advanced deep reinforcement learning techniques to train the artificial neural network, which essentially acted as the virtual rat's brain. They employed a method known as inverse dynamics modeling, similar to how our own brains are believed to control complex movements. For instance, when you reach for something, your brain doesn't individually control each muscle. Instead, it calculates the trajectory and translates it into the necessary forces and torques for smooth movement. In this virtual rat experiment, the neural network was fed with reference motion trajectories from real rats as inputs. Through deep reinforcement learning, it learned to generate precise patterns of forces that could move the virtual body's joints and muscles, replicating the natural movements observed in real rats. What's fascinating is that the neural network could generalize its learning to produce realistic rat behaviors and movements that it hadn't been explicitly trained on, showing broad capabilities akin to a biological brain. With the virtual rat brain successfully controlling the biomechanical model, researchers could delve into the neural network's activations and dynamics to gain insights into how real rat brains might control movement. Astonishingly, they discovered that the patterns of neural activity in the virtual brain closely mirrored neural recordings from actual rats' motor cortex and other brain regions during behavior. This suggests that the deep learning algorithm had uncovered internal models and principles of motor control similar to those in biological brains. For example, the virtual brain demonstrated the ability to switch between different operational modes based on context, resembling how real rodents' brains shift between behaviors like grooming, running, or rearing. Moreover, the researchers analyzed how the network handled redundancy in movement control. Since there are typically multiple ways to achieve a specific movement, how did the virtual brain choose the optimal solution? It seemed to employ a strategy that intervened minimally, making small corrections to conserve energy and avoid unnecessary force, aligning with theories of optimal feedback control used by biological motor systems. Another critical insight came from studying how variability, or noise in neural activity, translated into variations in the rat's movements. These structured patterns of variability offer insights into how the brain codes information, a perspective typically unseen when observing overall movements alone. This virtual rat brain represents a significant leap in understanding motor control and broader brain function. Unlike traditional methods limited to recording neural signals during behavior, this simulation allows researchers to explore and manipulate an accessible model of the entire brain-body control loop. Beyond neuroscience, this advancement holds promise for revolutionizing robotic control by reverse engineering the principles of biological intelligence that emerge from distributed neural dynamics. Researchers could potentially enhance robotic capabilities significantly. Imagine robots that adapt dynamically to their environments, exhibit versatile movement skills, optimize energy usage, and maintain robust operation despite sensor or mechanical failures. In conclusion, the virtual rat brain is not just a scientific breakthrough, but a gateway to exploring complex systems across various disciplines. It exemplifies a new era where simulations and AI accelerate our understanding and engineering of intricate systems, from neuroscience and biophysics to plasma physics and beyond. This work also highlights broader implications for fields like materials science, aerospace engineering, and even societal simulations, ushering in a new age of scientific exploration and technological advancement driven by advanced simulations and AI.